this video we will learn how to design spur gears. Here we will learn design of spur gears for its mechanical strength, for dynamic loading condition, and finally for surface durability. We will meet all these design requirements conforming to ACMA standard in a really simplified manner. So let's get into it. Before starting the designer will have following design requirements or design inputs. His gear should be able to transform one angular velocity to another angular velocity, RPM1 to RPM2, and it should transmit a specified amount of power. Also, there will be some space constraints, so his design should be able to meet that also. And most of the time, material of design is an input to the designer. So using this design data, the designer has to find out the following gear parameters, such as number of teeth on both the gears, and pitch circle diameter, and addendum and dedendum, face width, and tooth thickness. So these are the outputs we are expecting from a gear design. So let's see how we can deduce these values from this input data. We will start the design by considering the space limitation constraint. The designer can't design a gear of any size. If he does so, there can be two problems. First, the gear may not be economical at all. Second, the gear may not get fit into the space which it is supposed to get fit. So there is a space constraint while designing the gears. Assume the designed gear should come within this area, something like this. So the designer can obviously say if he sums pitch diameters of these two gears, it should be less than the allowable width, say 80% of allowable width. So this is one equation. And we also know the speed ratio of the gear. So we can write another equation like this. If we can solve these two equations simultaneously, we got pitch diameters of both the gears, dp1 and dp2. Next step, determination of number of teeth on each gears. First step, you have to assume a number of teeth t1 for small gear. Here I should say something to you. Design is an open-ended problem. There can be many solutions for a single problem, and all of them can be right. According to your first assumption, the design may change, but you have to start like this. If you know T1, you can find out number of teeth on second gear using this relation. And this term will be called as diametral pitch. Now we got number of teeth on both the gears, but still there is a small issue which has to be checked for. The issue of interference. Interference means if your gear has got profile below base circle, that won't be involute in shape. So if this portion of the gear comes in contact with the mating gear, it can cause material erosion and huge problem of noise. But you could avoid this interference if following conditions satisfies. If number of teeth on smaller gear is greater than this value, then there won't be any interference. So first check for this. If this condition is true, everything is perfect. You got number of teeth on both the gears. But if this condition is wrong, then you have to increase value of T1 and you have to redo this calculation again. And here AW means addendum value and phi is pressure angle of gear. And usually designers take pressure value of 20 degree. In that case you can take addendum of 1 module and dedendum of 1.2 module, and module is defined like this. Next, design for strength of the gear. or your gear should be able to withstand the force acting on the gear. Here F is a force acting on the gear, and it has got two components, one tangential and one radial. And this tangential component will induce a bending stress over root of the gear. And if maximum value of bending stress induced over here is more than the allowable stress limit, the gear will fail. You can avoid this kind of failures by designing with the help of an equation called Lewis bending equation. Before proceeding to the Lewis bending equation, we should determine tangential force first. You know, tangential force at the gear multiplied by pitch line velocity will be same as power transmitted. And you know the power transmitted, so you can solve for Ft. Now according to Lewis bending equation, maximum bending stress induced over here will be this. A pretty simple equation, but it has got one main problem. The value of L and T square. This is somewhat difficult to determine. So what we will do, we will transform this equation like this. In terms of diametric pitch and a term called Lewis form factor Y. The value of Y, Lewis form factor, is a function of pressure angle phi, addendum, dedendum and number of teeth. There are tables and graphs from where you can find out Lewis form factor value using these inputs. So from this equation you can solve for B or phase width of the gear. But if you design a gear using this equation, that will be so unrealistic, because here we are considering our gear like a cantilever. We are assuming it is in a static condition and we are designing, but that's not the actual case. So in next section we will see how we can modify this equation in order to incorporate many other factors which affect the strength of the gear. Here we will do the same design as we did in last section, but by considering so many other factors which will come into picture. So a more realistic approach. First factor is dynamic load on the gear. You know, as gears are rotating, you can hear some sound from the gear. This is because gears are clashing each other due to small gap in between, and this effect will increase load on gear more than its actual value, and that will be known as dynamic load, and there will be a factor to represent that, kV. It will be a function of pitch line velocity. Now the next factor, fatigue stress concentration factor. There can be localized stress on the root of the gear, and value of this can be much higher than the average value calculated from the previous method. So this factor accounts for that. And there are factors which will consider overload and load distribution on the gear, K and Km. Load distribution comes due to non-uniformity in the load. If you are supplying a uniform load, then Km value will be 1. Now considering all these factors, Lewis equation can be written like this. Value of all these factors are more than 1, so in effect these factors will increase the maximum induced stress value, and this is also called as mass strength equation, and general representation of this equation is like this. Here a new term J is introduced by rearranging the value of Y and Kf like this. So in fact both are same. So from this equation you can solve for value of B, which is phase width of the gear. With this we have found out all the parameters we wanted, but gear design is still not complete because of this reason. Even if your gear is having good mechanical strength, it may fail due to lack of surface resistance, and this is known as surface failure. And surface failure is explained in this diagram. If you push two cylinders with a force F, there will be shape deformation on the contact point, and this will lead to cracks and pits if your surface doesn't have enough surface strength. So you should check for that also. And the same phenomenon can happen for gear also. Here there can be cracks or pits due to surface failure. In order to make sure such failure doesn't happen, first you have to calculate the surface contact stress. And this stress is a function of all these parameters, and there is ACMA standard correlation available for this purpose. And if the surface contact resistance is less than a critical value, then your design is safe. Otherwise, you have to redesign your